So in this video, we are going to see IIR digital filters. So before going into the IIR digital filter, we are going to see what is meant by a filter. A filter is essentially a network that selectively changes the wave shape of a signal in a desired manner. The objective of filtering is to improve the quality of signal or to extract the information from the signals. A digital filter is a mathematical algorithm implemented in hardware or software that operates on a digital input to produce digital output. Digital filters often operate on digitized analog signals stored in a computer memory. Digital filters play very important role in DSP. Compared to analog filters, they are preferred in a number of applications like data compression, speech processing, image processing, etc. Now, we are going for the introduction of this IIR digital filters. So, the discrete time systems may be divided into two types. One is finite impulse response systems or filters, and the second one is infinite impulse response systems or filters. So first one, FIR systems or FIR filters. The FIR systems are the systems whose impulse response has finite number of samples. So they are called FIR filters. So what is FIR filter? So the FIR filter will be having only a finite number of samples. The impulse response of the FIR filter will be having only the finite number of samples. So the type of filters which do not employ any kind of feedback connection are known as non-recursive filters. So these FIR filters are also called as non-recursive filters. Why? Because it is not having any type of feedback. Next one, IIR. The IIR systems are system whose impulse response has infinite number of samples. So they are called IIR filters. The type of filters which make use of feedback connection to get the desired filter implementation are known as recursive filters. This IIR filters are called recursive filters. Why? Because it is having feedback connection. So the frequency selective filters. So the frequency selective filters pass only certain frequencies. So any discrete system that modifies certain frequencies is called a filter. So we concentrate on design of causal frequency selective filters. So first we are going to see the frequency response of low pass filter. So ideal low pass filter. So h of e to the power j omega is equal to 1 for w or omega less than omega c, and 0 between omega greater than omega c and less than pi. And this is a frequency response of the ideal low pass filter. So from minus omega c to omega c, it is having an amplitude of 1, and from omega c to the next value, it is not having the value of 1. So from omega c to minus omega c to omega c, it is having an amplitude of 1. So this is a frequency response of the low pass filter, ideal low pass filter. So next one, high pass filter. H of e to the power j omega is equal to 0 for omega less than omega c, and h of e to the power j omega is equal to 1 for omega greater than omega c and less than pi. So this high pass filter, it is having the amplitude of 1 from omega c to pi. From omega c to pi, it is having a value of 1. Next one, band pass filter, ideal band pass filter. So h bp of e to the power j omega is equal to 1 for omega greater than omega c1 and less than omega c2, and 0 for other values. So this is the frequency response of the band pass filter. So it is having the amplitude of 1 from minus omega c1 to omega c2. Similarly, from omega c1 to omega C2. Next one is ideal band stop filter. So the frequency response of ideal band stop filter HBS. BS means band stop. E to the power j omega is equal to 0 for omega greater than omega C1 and less than omega C2, and 1 for other values. And this is a frequency response of the ideal band stop filter. So the IIR filter design uses a technique of first designing the digital filter in analog domain and then transforming the analog filter into an equivalent digital filter, because the analog filter design techniques are well developed. The digital filter, since the digital filter designs are not well developed, first what we are doing is we are designing the digital filter in analog domain. We are designing the digital filter in the analog domain, and then we are transforming that analog filter to a equivalent digital filter. So when coming to the IIR filter design methods, we are having first analog filter design. We are having two methods. One is Butterworth filter design and Chebyshev filter design. So in transforming an analog filter into a digital filter, we are having three methods, and the first one is approximation of derivatives, second one bilinear transformation, and the third one impulse invariant method. So these three methods are used to transform an analog filter into a digital filter. The three methods are approximation of derivatives, bilinear transformation, impulse invariance method. So the system function describing an analog filter may be written as HA of S. HA of S is nothing but system function of analog filter. This A represents the analog filter. Okay. This A is nothing but this A is analog. It is the analog filter. And Y of S is nothing but the output, and X of S is nothing but the input. So system function HA of S is nothing but Y of S divided by X of S. So Y of S can be written as the summation of K is equal to 0 to M B K B suffix K and S to the power K divided by summation of K is equal to 1 to N A suffix K S to the power K. Here AK and BK are the filter coefficients. What is AK and BK? This AK and BK are filter coefficients. The impulse response of these filter coefficients is related to HA of S. What is HA of S? HA of S is nothing but the system function. So the impulse response is related to the system function by the Laplace transform. So HA of S is equal to integration of minus infinity to infinity H of t into e to the power minus st into dt. So we are relating the impulse response of the filter to the system function by the Laplace transform. For the stability and causality of analog filter, the analog transfer function should satisfy the following requirements. So the requirements are, the first one is the H of S should be a rational function of S. What is the first condition? The H of S should be a rational function of S and the coefficients of S should be real. The second point is the poles should lie on the left half of S-plane. So if the pole is lying on the left half of S-plane, it indicates that the system is stable. So what is the second point? The poles should lie on the left half of S-plane. The third point is the number of zeros should be less than or equal to the number of poles. So the third one is the number of zeros should be less than or equal to the number of poles. So for stability and causality of analog filter, the transfer function should satisfy the following three requirements. The first requirement is the h of s should be a rational function of s, and the coefficient of s should be real. And the second one, pole should lie on the left half of s plane, and the number of zeros should be less than or equal to the number of poles. For stability and causality of digital filter, the digital transfer function should satisfy the following requirements. The first requirement is the h of z should be a rational function of z, and the coefficient of z should be real. And the second point is the poles should lie inside the unit circle in z plane. And the third point is the number of zeros should be less than or equal to the number of poles. We know that the analog filter with the transfer function h a of s is stable if all its poles lie in the left half of s plane. Consequently, for the conversion technique to be effective, it should possess the following desirable properties. The first property is the imaginary axis in the s plane should map into the unit circle in the z plane. So we are going for a transformation from s plane to z plane. So during the transformation, the imaginary axis in the s plane should map into the unit circle in the z plane. Thus, there will be a direct relationship between the two frequency variables in the two domains. The left half of the S-plane should map into the interior of the unit circle centered at the origin in the Z-plane. Thus, a stable analog filter will be converted to a stable digital filter. The physically realizable IIR filters do not have linear phase. Okay. The IIR filter specifications include the desired characteristics for the magnitude response only. So now we are going for the comparison of digital and analog filters. So the first comparison is the digital filter. It operates on digital samples or sampled signals. In the case of analog filter, it operates on analog signal of the analog signal. Digital filter, it is governed by the linear difference equation, and the analog filter is governed by the linear differential equation. In the digital filter, it is difference equation, and in the case of analog, it is a differential equation. The digital filter consists of adders, multipliers, and delay elements implemented in digital logic, either in hardware or software or both. In analog filter, it consists of electrical components like resistors, capacitors, and inductors. In digital filter, the filter coefficients are designed to satisfy the desired frequency response. In analog filters, the approximation problem is solved to satisfy the desired frequency response. So, the advantages of digital filter: the values of resistors, capacitors, and inductors used in analog filters change with temperature. Since the digital filters do not have these components, these digital filters will be having high thermal stability. In digital filters, the precision of filter depends on the length of the registers used to store the filter coefficients. Hence, by increasing the register bit length, the performance characteristics of the filter like accuracy, dynamic range, stability, and frequency response tolerance can be enhanced. The digital filters are programmable. Hence, the filter coefficient can be changed anytime to implement adaptive features. A single filter can be used to process multiple signals by using the technique of multiplexing. The disadvantage of digital filters: the bandwidth of discrete signal is limited by sampling frequency. The bandwidth of real discrete signal is half the sampling frequency. The performance of digital filter depends on the hardware. That is, depends on the bit length of the registers in the hardware used to implement the filter.